Okay, let's take a look at question number 18, which we are provided with a force versus time graph and a spacecraft of 4,000 kilograms. And we're told the engines are fired and that this is resulting force versus time graph. Um, we are ultimately asked uh, what, which of the following responses is the best estimate of the net change in speed of the spacecraft. So uh, first of all, we have to recognize that the data here is a little bit spotty and kind of not perfect. So that's why they're saying best estimate. It's also a clue to you to be kind of casual in a way in terms of your computation and not to be too hung up on exact numbers. So whenever you're asked for a best estimate, you can trust that the answers will be distinct enough. And here you see plus and minus zero point 0.1, plus and minus zero point 0.4 are the responses. So the difference in sign is important, and the difference in magnitude is a factor of 4. So you don't have to have a number that's perfectly exact. So how do you go about thinking about this particular problem? Well, I would suggest that there's two things you need to recognize. If you're going to eventually figure out the change in speed, okay, you're going to want to know what the change in momentum is. And since we know the mass, if we know the change in momentum, we can find the change in velocity. So the two things that I would think about is that the impulse is exactly equal to the change in momentum. That's something that we learned a while ago. And in its simplest form, with a constant force, that impulse is a force times a time. But in the case where the force is not constant, and that's certainly true here, right? The force is changing over the 4-second interval. During that time, we could figure out the impulse by getting the area of a force versus time graph. So we're going to look at this geometrically, get the area. We'll let that equal the change in momentum, and that change in momentum will help us find the change in the speed of the spacecraft. So here we go. We look at this triangle that I've superimposed on this data from 1 to 2 seconds. It's not a perfect triangle, but it's pretty close. And it gives us an estimate of a positive area during 2 seconds, the first 2 seconds. From 2 to 3 seconds, there's no force, essentially, so there's no contribution to the area there. And then from 3 to 4 seconds, the rockets must fire in a different direction, and they create a negative force, and therefore a negative area in this little rectangle here. So we could do this in our head. This is a positive area, and it's 1/2 the base times the height. Well, 1/2 the base is just 1/2 times 2, that's 1. 1 times the height is 1,000, so the positive area here is 1,000. This is a rectangle that has dimensions of 1 unit of time here and minus 500 units of force there, so that's minus 500. Minus 500 plus 1,000 is a net area for the whole 4 seconds of plus 500 units. So that's our impulse. It's the area of the force versus time graph is 500 units of change of momentum. The impulse is equal to the change of momentum. And if I take that impulse, that change in momentum of 500, and divide by the mass, I'll get a change in velocity. Now, I've got 500 divided by 4,000, which is a little bit more than 1/10, but not a lot more, and certainly nowhere near 4/10. So it's a positive number, and the change in velocity is approximately 0.1 meters per second. So that's the way to think about that problem, is to think about impulse as an area issue, and then impulse leading to change in momentum.